This lesson is for section 11.2 and 11.3. We're going to be talking about Gaussian elimination and matrices. So the first thing I want to talk about is what Gaussian elimination really is, and it's simply a method that helps you solve systems of equations that are not 2 by 2 systems. You can use Gaussian elimination for a 2 by 2, but really it's typically used for a large system, in 3 variables or more. So I have an example here. The first example is something that's already in triangular form, which is what Gaussian elimination, that method, the whole point is to try to put it into triangular form. So it's called triangular form, and you can see here that the variables here form a triangle. And in this case, this problem becomes very simple because I can use something called back substitution in order to solve for my missing variables. Since z is equal to 3, I can simply plug that into here to obtain, let's see, 3 times 3 equals 11, so y is going to equal 2 here. And then once I have y equal to 2, I can plug in y equals 2 here and z equals 3 here in order to obtain the x variable. And in this case, 5x plus 8 minus 3 is 5x plus 5. Subtract that 5, and I end up with x equaling -1. So I have a unique solution. -1, 2, 3 is the solution that satisfies every single equation in my system. So as you can see, this next problem, number 2, is not in triangular form. So we're going to use Gaussian elimination here in order to solve this system. Okay, so Gaussian elimination is just a method that allows us to rewrite and convert a system into triangular form. So we're going to just use operations on our rows here, and I denoted each row as A, B, and C. But we're going to do operations on these rows in order to eliminate variables so that I can get it into triangular form. Okay. Now I notice that I want to get rid of the x terms here in the leading coefficients here. I want to get rid of these and make those 0. And since I have this line here down at line C here has a +1 here, I'm going to keep that line untouched. That'll be for my triangular form. This will be the line that I keep throughout the system because it already has a +1 coefficient. So that means I'm going to work to get rid of these 2 coefficients here. So I notice that if I take A, line A, and I add 3C to that, I'll eliminate the x in line A. So showing that calculation, here is now my new line after doing that. So it's really just regular elimination here so far. Now I also want to rewrite this so that I have my new system here. So I've just rewritten the system so far. This is the first step in Gaussian elimination, where I've taken line A and I've eliminated the variable x from this and rewritten it here. Now I notice I can take half of that line and just in terms of getting a smaller coefficient. So this is not a necessary step, but it is a helpful step. So I'm just working with smaller numbers here because I noticed that everything's divisible by 2, so I'm just going to divide out the 2 here. Okay, now I'm dealing with this new system. And now if I want to eliminate the x in the second row, I can add -5c plus b. So I can multiply this line here by -5 and add to that this line here to eliminate the x as well. So here's the work for that. So I have this new line, -13y plus 5z equals -34. So my new system now, if I were to rewrite this, so taking this line here, performing these operations, I now have this new line for the system. So far you can see I no longer have the x at all in terms of the first 2 lines, and I still have this one untouched. Okay. Now, in order to keep it going further into triangular form, I need to have a coefficient of 1 in front of one of these y terms. Now, I could just divide by 7 here throughout, or -13 throughout here, but then I'm going to deal with some fractions. So what I actually notice is if I double this line here, I'm going to be left, if I add the 2 lines together then, I'm going to be left with a single y, 1y. So I want to, instead of eliminating a certain variable here, if I add 2 times a, so like I said, doubling this line here, and add b to that, I now am left with y minus 7z equals -4. So after performing that operation here, I can substitute this second line now as y minus 7z equals -4. Okay? So I'm just now getting, in terms of my coefficients here, I have 1x, I have 1y, there's no x term here, so this is getting closer to triangular form. Now, the last part I need to do is be able to get rid of this 7y here, and to do this, I notice that if I multiply -7 times this second line here and add that to the first line, I will be left with 43z equaling 43. So now my new system, after I substitute this new line in here, after doing this operation, a plus negative 7b, I end up with 43z equals 43. And of course now I can multiply by 1/43 on line A to end up with z equals 1. So now I have this in triangular form. Okay, upper right, oh, this is lower right triangular form. But now I can actually use back substitution to solve this system quite easily. So obviously with back substitution, I plug in z equals 1 into here. Once I get that variable y solve for, then I plug that back into here, the 1 into here as well, and I solve for x. So you end up with a solution for x, y, z, the point -2, 3, 1. Okay? Now, there was really nothing special about what I did here in order to put it into this triangular form here. I could have done a lot of different computations here and done with different orders, different rows. Basically, all I did was stuff that I thought was the easier thing to do. Just like in any substitution or elimination problem, you could always do a number of different steps in different ways to get to the same solution, but it's about becoming, efficient and finding the easiest way to do that. So I just thought what the steps that I took were the easiest ones that just popped into my head, kind of. We could have left it in triangular form and used back substitution, but I'm going to take it a step further here and try to get it down so that I have, here I had z equals 1. I want to know what y equals and x equals, still applying Gaussian elimination here. So I did a few more operations. I'm not going to go through every single step, but eventually I end up with this system here, where I have x equals -2, y equals 3, and z equals 1, which is what we said we would get when we did the back substitution as well. But hopefully you're noticing that if I just reorder the system a little bit, I actually have something that looks very similar to row reduced echelon form, which is something that your calculator can do for you. So basically I went through this Gaussian elimination, showed you the algebraic steps that your calculator essentially does for you in like a millisecond. So we're going to use our calculators to solve 3x3 systems. I'm going to show you a couple different things, but you still need to know how to use Gaussian elimination and apply that. Essentially you're just ordering and doing operations on multiple rows, adding, multiplying rows together. That's about it. Okay, so I don't expect you to write all of that stuff down because, like I said, we're going to do that with our calculator for problem 2. But first I want to talk about matrices in order for you to be able to plug this into your calculator. I want to review matrices, and then we're going to come back after you do some stuff without a calculator, and then we're going to talk about matrices with a calculator. I want to start by talking about the dimensions of a matrix. So a matrix is just a way of organizing data. Now in this case, this matrix is a 3x2 because it has 3 rows and 2 columns. So whenever you're talking about the dimensions of a matrix, you go by rows, 1, 2, 3 rows, and 1, 2 columns. So this next matrix here is a 2x3, and lastly here we have a 3x1. Now when you add or subtract matrices, they must be the same dimension in order to add them, and all you're going to do is look at the position of the matrix or the element in the first row of each first column, and you would add those together because that's the operation that we're doing here to get 1. 1 plus -9 gives me -8, 3 plus 4 gives me 7, and so on. So I could fill out the rest of this. I think you get the point. Now when you do a scalar multiplication of a matrix, for example here, you're just going to distribute that -2 to each one of these terms here, so that new matrix becomes +2, +18, -8, -20, -14, and 8. Now I simply add that to the original matrix here that was listed first, just like we did in this problem here. So I'd end up with 2 plus 2 to give me 4, 1 plus 18 to give me 19, and so on. Okay. Now in problem 8, this is an example of something that you cannot add because these dimensions are not the same. Okay, they have to be in the same position in order to be able to add the 2 elements in the matrix. Now, to determine if you can multiply matrices, okay, not matrix scalar multiplication, but actually multiplying 2 matrices together, you need to make sure that the dimensions match up. And to figure that out, you're first going to list the dimensions of each matrix. So this is a 2x2 multiplied by a 2x2. Now, if the dimensions of the middle numbers match up, then this is able to be multiplied. And your resulting matrix will be the outside dimensions here. So you're going to result in a 2x2 matrix when you multiply these 2 matrices together. And to multiply matrices, this is a sort of a difficult process the first time you see it, but I know this is a review for you, so I'm going to go through this kind of quickly. But you basically multiply row here in this first matrix by a column here in this second matrix. So that the result of the product here in the sum of these two parts is what goes in the first position here in your new matrix. So you have 4 different, I guess, blanks that you can write into your matrix, since you know it's a 2 by 2. And in this first position here, I'm going to multiply 5 times negative 12 to get negative 60. And then I'm going to multiply negative 7 times 2 to get negative 14. And then I'm going to add those two numbers together to give me negative 74. That's the number that goes in the first row, first column. Now when I find the second, or the first row, second column, so this would be R1, C2 if you wanted to abbreviate that, to find the number that goes in this position, what I'm going to do is take that exact same row that I had before, and I'm going to multiply it by this column here. So now I take 5 times 3 and add negative 7 times 0 to get, when I add those together, 15 and negative 7, I get a positive 8. Okay? Now I'd repeat that same process. If I had more columns, like 2, 1, 3, 5, and I had more columns here, I would take that same exact row and multiply it by each of these columns and continue throughout. But I've exhausted all the columns, meaning there's only 2. I've exhausted both of those. So now I go to the next row. So now I'm focusing on this row, 1, 4, and multiplying it by this particular column first. So now I take 1 times negative 12, 1 times negative 12 here, and I add to that 4 times 8 to give me negative 4. And I do the same thing again with the same row and multiply it by this column here. So I get 1 times 3 plus 4 times 0. Okay? Oops, put it in the wrong spot. Anyways, that's 7. So this is the new matrix that I get after multiplying those. Now in problem 10 here, to decide if we can multiply these, again, you would take the dimensions. This is a 2 by 2 multiplied by a 2 by 2. These match up, so it can be multiplied, and your resulting matrix will also be a 2 by 2. So I can set this up very similarly to what you just saw here. And I want you to notice this is the exact same matrix, just the order has been changed. So the matrices are the same here, the order is different, and you're going to get a different product for this because matrix multiplication is not commutative. Did I say that right? Commutative, sorry. So negative 12 times 5 gives me negative 60 plus 3 times 1. And the second column here, I'm going to multiply the first row, second column, to get positive 84 plus 12. And then I move on to the next row. Next row here is going to be 20 times 5, 1. So I have 2 times 5, 10, plus 0 times 1, 0. And lastly, that last row with the second column here gives me 2 times negative 7, negative 14, plus 0, 0 times 4. Alright, that results in a new matrix, negative 57, 96, 10, and negative 14. Now, in problem 11, sorry, the whole point of this was to show that these are not the exact same. Okay, so matrix multiplication is not commutative. Okay, alright, number 11. To decide if we can multiply these, remember you have to look at the dimensions. This is a 3 by 1 matrix multiplied by a 1 by 2. So we can multiply these. Middle digits match up. This actually is going to give us a 3 by 2 matrix. So 3 rows, 2 columns. Okay. So I know that sounds kind of strange since you're not dealing with too many numbers here, but you're going to take the first row, multiply it by the first column. You would find the sum of that. There's not more than one number to multiply here, so that first number is just a 3. Then you're going to take the first row and multiply it by this column. Once you've exhausted all your columns, you move on now to the next row. So now we're going to take 8 and multiply it by 1. I get 8. Take 8, multiply it by the second column here, that's 72, and so on. So then I get negative 13 times 1, and negative 13 times 9, give me negative 157, okay? Oh wait, that's way off. Sorry, 27, negative 117, sorry. Okay, I know I went through that kind of quick, so just go back and review the matrix multiplication. Try these problems. Definitely try these on your own. Make sure you can multiply the matrices in the first place, and then go from there, setting up your, your blank spaces, I suppose, if you want to do it that way, and then find the appropriate matrix. Okay. Alright, so now that you know the basics of matrices, I can go into inverse matrices and row reduced echelon form with you, these two methods for solving this particular system with using your calculator, but I first want to talk about the different types of solutions and the different types of systems that you're going to see throughout this section. So here are some examples of the different types of solutions and the different types of systems that you're going to see. We can either have consistent or inconsistent systems. So I want to talk first about consistent systems. Now, the most difficult problems that you're going to be shown are ones where they have a consistent system and there's infinitely many solutions. And in this case, you're going to have to do stuff by hand. Your calculator is not going to be able to do all the work for you. I'm going to get to an example like that. Now, this would be an example where three planes here intersect, and they're going to intersect to form a line. So let me draw that line in right there, roughly through here, okay? So you're going to be able to find the solution in terms of that line and rewrite your system in terms of that line. Now, another type of consistent system is when you have exactly one point in common to all three planes. So notice that all three of these planes here intersect exactly at one point. And that's the example that we showed you, the Gaussian elimination example, where we ended up, I think it was like -2, 3, 1 was the solution to that system. So that has exactly one system, exactly one solution. Now you can also have inconsistent systems, and an inconsistent system sounds exactly like it, the word sounds like. It doesn't have consistency to it. I'm just being redundant here. But basically, you could have your planes intersect, but they don't have a point in common. So there's no one point or one line where these planes all intersect in common. Or you could have parallel, all three parallel planes, or you could have maybe two planes parallel to one another and a third intersecting both, but not at a common point. So these would represent solutions or systems, with no solution, okay, which is why we call them inconsistent. And these are the easier ones because as soon as your calculator is going to show you that it doesn't have a solution, you stop right there. You just write no solution because it's inconsistent. It's when you get to a problem like this where it becomes a little bit trickier. Okay, so let's finally get to using our calculator to solve problem 2 here, all right? Now, what I'm going to show you first is inverse matrices, so this first part over here. And I've already set up the matrices in terms of what you should show as far as work. We have our, this should not say constant, sorry, this is our coefficient matrix, where we take all of the coefficients in front of our variables here. So notice I'm just transferring that here. Our variable matrix, x, y, z, and if this was a 4x4, you would have 4, variables. And our constant matrix, 6, 6, 8. So our constants come from here. Now, hopefully you're realizing that the reason why you can rewrite it like this is if you multiply this times your first column here, then you would end up with this line. This would be the sum of those terms in terms of like just multiplying it by hand. So this shows this same system here just with the matrices. Now I'm going to define this matrix as A. This is going to be my constant matrix, or my variable matrix. I'm going to call that matrix X. And let's call this B. So in my calculator, I'm going to input matrix A and matrix B. Now algebraically, right now we have matrix A times matrix X equal to matrix B. If I wanted to isolate my variable matrix here, I would divide by A, right? That's what we would typically want to do algebraically. Well, there's no dividing matrices. What you can do, though, is multiply by its inverse. Now, multiplying by a matrice's inverse gives you the identity matrix, 1, 0, 0, 1, and this is what you're looking for. In this case, it would be, 1, 0, 0, 0, 1, 0, 0, 0, 1, but it gives you the identity matrix. All stuff, again, it's under review. This is all review stuff from before, but I just want to re-mention that. And this will isolate that X, this variable matrix, for me. Now, on the other side, if I try to multiply B times A inverse, these are not matrices that I can multiply because the dimensions don't match up. This would be a 3 by 1, right? This is matrix B, a 3 by 1, multiplied by matrix A, which is a 3 by 3. And since those inner dimensions don't work, it won't work to do it in this particular order. So instead, I switch the order. I multiply by A inverse B to isolate this X. So this is going to go away because it's just the identity, to leave me with X equaling A inverse B. So this is the algebraic reason why inverse matrices work. But essentially from here on out, I'm just going to type this and plug this into my calculator. So I go to second matrix, I scroll over to edit, and inside here I'm going to change the dimensions of this matrix. For matrix A, I'm going to make this a 3 by 3, and then I'm going to input all of those values. Alright, now I already filled in matrix B here as well with our constants, 6, 6, and 8. So on my home screen here, what I'm going to do now, after I quit out of that, is hit second matrix A, hit enter on this, then the inverse key, which is right underneath the math key, and then second matrix B, and this will result in my matrix here. Ooh, okay, now the fact that I didn't get the exact same answer that we got with the Gaussian elimination means that I probably made a mistake in typing in and entering my coefficients here. So this is why it's really important for you to, one, label all of your matrices, because it's really easy to type in something incorrectly and get the wrong answer. So what I'm going to do to test to see what I did wrong is I'm going to hit second math here, or second matrix, sorry, and hit A, and then I'm going to see the values that I typed in. I have -3, 2, and then see this mistake here, this -6. If I go back and change that to a -6, which is what it's supposed to be over here, I have in the coefficient matrix here, -6. If I go back to that and edit this and change that value, I don't have to re-enter everything all over again. I can simply go back to my home screen and hit second entry here. It'll bring up what I last entered, which was A. Hit it again, and it'll bring up A inverse B for you. If you hit enter this time, now we'll get that exact same solution, -2, 3, 1, that we already got. So I just wanted to show you this in terms of how to solve that. Now, for the second example problem that I have here, you're going to see that using inverse matrices doesn't actually work for the second example. So I'm going to go ahead, and you should too, plug all of this into your calculator and try to practice this one more time. But you're going to get an error message here. Okay, so I've already edited matrix A. I've already done matrix B too. I just wanted to show you that when I go and type in second entry here and pull up A inverse B, this time I get this weird message that says singular matrix, an error message, and that's because or this is where inverse matrices kind of has its flaws, because I can't tell whether or not this is an inconsistent solution or an inconsistent system, like we talked about just prior to this, or if it's a dependent system where you have infinite solutions. So this is where this kind of solving kind of runs into some issues, okay? So it's better to use row reduced echelon form, and I think you guys are going to just like it anyways because it's a little bit faster, but row reduced echelon form is the one that's most similar to Gaussian. This is the one that does all of that Gaussian elimination for you, okay? So I'm going to take the matrix that I already had that was similar, second matrix A here, but I'm going to edit this just slightly. I'm going to make this a 3x4 matrix now. Okay, so by making it a 3x4 matrix, I don't lose any of those coefficients here. And then I'm going to slide over to this last position and include the constants there. So -4, 13, and now -33 are going to be included in this matrix. So I have a 3x4, and I can scroll over to see the whole thing. All right, this time in your home screen here, so you quit out of that, you're going to hit second matrix and scroll over to math and all the way down to RREF, row reduced echelon form. Okay, oops, I went past it a little bit. So I just have to type in this once and then second matrix A and hit enter, and now I get something that I can actually interpret. So this is the resulting matrix, right? Notice that it is putting this into Gaussian form for you. The only thing though is that I have in the very bottom here a true statement, but essentially what this is saying is that 0x plus 0y plus 0z equals 0. This is true, right? This is how we know that this is a consistent system, but that it has an infinite number of solutions. Okay, and this is the one that I said was going to be the hardest for you to have to write, because you're going to have to now be able to interpret this and write this in terms of one single variable. Okay, now if this system, and I'm going to change this for you real quick just to talk about it, if this had been 0, 0, 0, 1, then this is a false statement. 0x plus 0y plus 0z, in other words 0, cannot equal 1, in which case then this would be an inconsistent system, and you can stop and just say no solution. And you're finished with the problem. However, like I said, this problem is a little bit trickier because it is a true statement, and we now have to figure out what the equation of the line is in which these three planes intersect. So what we're going to do in terms of one variable is call, it's usually easiest to just do it in terms of z, but I'm going to look at, I can do the original system here, there's a little bit more work to do, but I just want to take these two lines here, because this is represented as x plus 3z equals 10. That's what this first line here says. And the second line is y minus 5z equals -7. This is what I get from my system, or my resulting matrix here. Now, I'm going to write my answer in terms of z, which means that I'm going to solve for the y here as well as the x, so that I have basically x as a function of z and y as a function of z. Okay? So if I do that, I end up with y equaling 5z minus 7 and x equaling negative 3z plus 10. Now sometimes you're going to have to do a couple different substitutions so that you have all z's, in there. This one was a little bit easier because I didn't have a variable here for the y, so it dropped out. But anyhow, after I get x, y, and z all in terms of z, I can simply write this as an ordered triple, like so. Okay? So that's eventually what I'm going to write. So let me erase this down here. My final answer then for this problem is negative 3z plus 10, 5z minus 7, and z. So this is rewriting this system in terms of the variable z. Okay, this is what we expect you to be able to do when you get a solution with a system with infinite solutions. Okay, so you will be assessed on this. Make sure you understand this. Like I said, make sure you go back, replay that. But that's the end of the lesson. Thanks for doing a great job.